Hello and welcome to 3D Vision Technologies 10-4 Tech Talk, a monthly introduction to engineering technology that can make your company better, faster, and smarter. I'm Todd Majeski, your host for today. Today's topic is reduced time to market with 3D printed injection molds. Our guest speaker is Jeremy Marvin, application engineer for 3D Vision Technologies, 3D Printer Group. Jeremy works out of our Cincinnati, Ohio office and has been with 3D Vision for almost 5 years. Welcome to the show, Jeremy.
Thanks for having me.
And before we get started, I want to remind the audience that this show is being recorded and we'll send an email with a link to go back to this presentation in its entirety. Also, we'll be answering questions at the end of this 30-minute presentation, so use that chat window in the lower right corner if you have a question. Okay, so let's get started. So Jeremy, before we really jump into it and start your presentation, let me ask you two questions that everyone might be thinking. First one, who is this presentation geared towards?
So this presentation is going to be mostly geared towards people that design product, plastic product, people that design the tooling for that product, mold makers, and PIMs, or plastic injection mold house, the manufacturer of those products.
Yeah, contract manufacturers, great. And my second question is, why should I listen to this presentation?
If you feel that that runoff or that setup is too long to get to your, taking that tool steel mold and running it off, getting it set up, if that's too long, you want to reduce that time, this is going to be for you.
Yeah, getting your product to market faster. So that's what it's really all about, in saving money. Okay, so let's just turn the presentation over to you and let's get started. So, oh, by the way, I want to tell you, Jeremy, I might be asking you some questions throughout this presentation, so don't be shocked if I kind of interrupt.
Feel free.
Thanks.
All right, so just a quick agenda before getting too deep into it. It's going to flow a little bit like this. We'll have a general application overview, just a high-level overview of what injection molding is, I'm not sure where the audience is going to fit into those four categories or maybe outside. A process comparison, a very, very high-level overview of the injection mold process, starting from the product design all the way over to that production run, and then we'll see where additive manufacturing fits into that. And then we'll go over the benefits of doing that and finish off with a customer success story and an overview of what injection molding is. So we said before, anytime you want to mass produce plastic parts, and we're talking hundreds of thousands or millions or maybe tens of thousands, anytime there's a plastic part involved, we're usually talking injection molding as long as the quantities are enough. I'm looking down at my computer, I see all the keys, I see the housing of my laptop, I see my mouse down here on the table, all the buttons on that. Those are all injection molding.
And those are also millions of parts, too.
Millions and millions of parts. And we need a high volume, and people like it because it has good repeatability. Parts that were printed at the beginning of the run are going to match the parts at the end of the run. And even, look at the Lego here, my 7-year-old has Legos that she just got, she loves playing with them, and I still have all my Legos from 35 years ago.
You still have your toys?
I still have some of my toys, yes.
You are a geek.
I still have all my Legos, and those pieces fit together. So good repeatability and good dimensional stability. Right. So the mold itself is traditionally made out of some high-grade metal. It includes the cavity or the negative of the plastic parts. We have, if you can see those tubes on there, those are usually the cooling lines. If we're trying to cool it down really fast to get our production rates up. We also have gates and runners, which is the paths that the plastic would flow throughout the mold. We have, even for some more high-end molds or some more complex molds, we'll include cams and slides or to allow the mold to break apart, if you will, automatically to allow it to pop out. And then we use an ejection system to get those parts out of the molds. So where would we see that? Anywhere, like I said, anywhere where we have those plastic parts. Consumer products and electronics, automotive, aerospace, electronics, toys. Any company that would be in any phase of the production of those plastic parts, either a tool and die shop, OEMs, custom molders, service shops, anybody that does high volume plastic part production. Okay. So let's step through that, just a high level stepping through of that traditional process. So we mentioned that we're looking for, that we're touching on the part design. So something that kind of clicked with me lately is when we're talking about injection molding, it's not really talking about the tooling. It's that part, that end part that comes out of the mold. So we need that part designed somehow, some way. And that part is going to be handed off to a tool designer, or maybe these guys are the same guy, who knows. All right. From there, you take your tool design, and once the tool design is done, you're going to manufacture that. And what we've seen here is everybody is manufacturing with CNC. Automated machinery to manufacture those. From the manufactured tooling, we're going to mount that up onto our injection mold machine. I've got some pictures here of a couple of injection mold houses, and you can see rows and rows of injection mold machines. We'll mount that tool. We'll slowly dial in and narrow down the injection parameters to get to where we need to. Maybe not injecting 100% of the pressure or the volume of the plastic that we need.
So that's the PIM right there, the plastic injection molder.
Yes, exactly.
Yeah.
Okay. So once it's molded and we get a few good parts, we will do that first batch, that trial run. So you mentioned you were in the mold maker, and you got asked a lot to produce those sample parts.
Yeah.
So people will ask for different numbers of quantities, and to prove it out, if there's a revision at this point, so pretend that it's a CNC tool steel mold, any changes or errors that are found now is going to dramatically increase the cost of that part run, all right, and usually requires some skilled labor. So where does 3D printing fit in is getting these sample runs, and even going back one step further is to dialing in that process.
So you're saying that if we print the tooling versus having it machined, we're still going to have it machined, correct? Or can we eliminate a metal mold altogether?
So that depends.
Or am I asking this question too early?
No, I think this is okay. So if the quantities are low enough to warrant the price, so if you only need a couple hundred, absolutely we can replace that metal mold.
Yeah.
And that's going to reduce reduce the cost and the time to get to that point.
Okay.
Okay.
But if you're doing large quantities,
yeah, the sweet spot would be in that 5 to 100.
5 to 100. Okay, got it.
Yeah, and it would take multiple molds if you want to go more than that. So going on to the polyjet process. So stepping into the polyjet process a little bit, so we have a zoomed in part of the machine, the polyjet machine. We're laying down or misting out micro droplets, micro down to the micro level, very, very small. Any overhangs are going to have a support structure build up, and it's all based on acrylic. We mist it out layer by layer, and we're going to cure it instantly with a UV light.
So solid that with that level of droplet and micron, you're going to get very fine detail.
Very, very fine detail. And that's one of the benefits that people like with polyjet technology, is because of that excellent small detail, the great surface finish. And also to know is we're still going to need that 3D CAD model.
Mm-hmm.
So we're going to load it and print that out. Okay, so we've got our machine, we know how it works. Let's talk about materials a little bit. As far as polyjet technology in general goes, we have lots of materials available to us. And I think if you look at the spec sheets, it's upwards of thousands of materials and different mixtures of them, from medical grade to rubbers, simulated polypropylene, to the bright, vibrant colors of opaque, rigid parts, and then the translucent, almost crystal clear glass.
And so I see a lot of these materials. These are all the options that the polyjet technology can print out. But what's the best plastic, or what's the best material specifically for making a tool?
For injection mold tooling, we want to be on the top of this list on the engineering plastic, specifically the digital ABS over here on the side.
Mm-hmm. And why that material?
So digital ABS it's a composite material. A composite is formed by combining materials together that are different, that combines and creates a structure that is better than the sum of their components.
So we're digitally creating. Okay, now I might be going off the script here, but so it's because we're digitally creating a plastic part, we're making it stronger than what you could from just one homogeneous. Is that correct?
Exactly.
Now I know there's other 3D printing technologies out there and they use they have to make the material. You're using a single vat of material, and you can't blend things together unless you buy their version of their material. So can you vary that structure at all?
For the most part, no. It's all automated within the printer itself. I can't control like how it's blended together. I mean, it's supposed to be quick and easy. Where I load the part, I choose that I want digital ABS and print.
Okay, got it. But it makes a stronger part.
It makes a stronger part. So we talked about blending the materials together in a structure that we would call a composite. All right. So here with the digital ABS, we have a high temperature material. So when we're talking injection mold, we're talking a couple hundred degrees. Right, so we need that high temperature, and then we want a high toughness. So we have an impact, and we have that pressurized plastic flowing through it. So we need both of those properties to get where we need to go. So PolyJet, it's not going to fit 100% of the injection molds out there. It has a sweet spot that it likes to be in. So for the most part, we want to be in a reasonable molding range, the temperature range. You know, we do have an HGT we have to worry about. And we like to be below 570 degrees Fahrenheit with something that flows very well. Some good candidates of that would be polyethylenes, polypropylene, polystyrenes, ABSs, and polycarbonate ABS blends, and then even some glass-filled resins.
So if product designers, if you're listening and you're making parts now using any of those materials, then printed injection mold or printed tooling would be a good candidate for them, right?
Absolutely.
Okay, got it.
All right. So we mentioned the quantities before. We want to be in that low quantities, you know, maybe to that proof that the design is correct, to maybe that's all you need is 100 parts. We want to be in the mid-size. So I know that some of the automotive people will use, you know, presses in the hundreds of tons. We want to be in that 50 to 80 ton range is our sweet spot. And anywhere where you want to have confirmation that the design is right before cutting steel.
So do you think a client could do this, one of our audiences, they could say, well, maybe my ton size fits correctly and I'm not going to make hard tooling. I'll make this, I'll call it soft tooling or plastic tooling, prove out the part, then go ahead and commit to hard tooling.
Yes,
okay.
Absolutely. All right. So the benefits of doing this is we're getting, you know, a prototype of the part by our design and in the true material. All right, we're going to see that we could save time and money, you know, 50 to 90% of the cost involved with that, and it's so automated. You know, in your CAD, you're saving out that STL and the object software. We're loading it, we're doing orientation, and we hit print. That's it. There's not a whole lot involved with getting it done.
Is there a size limitation to the part? I mean, it sounds like the 50 to 80 ton was your range for injection molding, but is there a size limitation to that? Like, could I do a part that's maybe, you know, 12 inches by 12 inches?
As long as the printer was big enough to print the mold for that,
I
think most definitely. And I think we have a printer, and we might see a picture of that here later on that can handle that.
Okay, got it. So it's not just for small parts?
Not just for small parts. All right, so we're going to be a benefit in the early detection phases where we will find the flaws in the part and the tool, and definitely we want to test out the thermoplastic performance to maybe make sure that we chose the right plastics. So who's doing this right now? Who's already printing out their molds for that trial run? Nipro is a healthcare company. They're an injection molding, and they do some contract manufacturing. Soifer, they do sensors and controls for automotive and consumer goods, consumer appliances, and we'll talk about them a little bit in our customer story. Grundfos is a pump manufacturer. Berker switches, Rutland Plastics is an injection mold. Whale, I think they do water and heating systems, and they might do some pumps. Diverse Certified Plastics is a custom mold shop. Worrell does medical devices, and we've all heard of Unilever with some consumer goods.
So it looks like we have a good mixture of not only product design companies, but also we have contract manufacturers.
Yes.
That just print parts, or basically, injection mold parts for customers.
Yep. We've got a little bit of everything, so hopefully we've got somebody here that anybody can relate to. Okay. So Robert Soifer Company, they've been around for a long time. They produce plastic parts, as I said, for the automotive and household appliances. They produce 12 to 15 million plastic parts each year.
Mm-hmm.
And because they use plastic parts on their process and to their equipment, is they outsource a lot of it. So they actually buy just as many plastic parts from their suppliers. And they have annual sales of over $113 million annually.
Okay, so they're a good size injection molder.
They're a pretty good size.
Yeah.
So the part that is in these pictures is a plastic enclosure for some electronics, I believe.
And I see that on your slide it shows pre-production parts. So these are test parts that will go to the company, so they'll assemble it, make sure everything fits.
Everything fits, and I believe we have, I think we actually have one of these molds in-house, and it was before they found a design flaw.
Oh, got it. Yeah. Which that can be costly if they cut hard tooling.
Uh-huh.
And everyone I know who's done plastic parts knows once you rework a tool, the cost is enormous.
So the business they needed pre-production parts. They needed to test the performance of the thermal and mechanical loads with that true plastic in their real-world materials. Okay, so their traditionally machined mold cost them $53,000 and took them 56 days.
There's your months.
There's your months, all right? And can you imagine waiting 56 days to find out that the design was incorrect or something wasn't quite right? All right. So they have incorporated polyjet tooling in all of their product development. So every part that comes out of there that's a new develop gets polyjet tooling for test runs. All right. So the polyjet tool material price alone was $1,300 and took them 2 days to get. And I believe they have one of the smaller of the Connex printers, so a bigger printer that can technically reduce this time even further.
So here's a client that actually owns a polyjet printer, and they're printing their tools and running them. So it took them 2 days and about $1,300. Well, let's say one of our people in our audience don't have a printer and they want to print a tool. They could outsource it to, say, someone like 3D Vision or maybe one of these service bureaus that are out in the industry. How much would that cost for them to make that same tool?
So that depends on how long it takes, and the material used is kind of the ratio. And what we've seen is either 4 times the material cost up to 6 times the material cost, depending on the geometry, how long it takes, and if the machine is available for anything else. So if I can print this mold and get a couple other parts on the tray, maybe it's a little bit cheaper.
Gotcha. So anywhere between $6,000 and $8,000 to print that same tool if they outsourced it.
Exactly.
Okay.
Yep.
That's a huge savings, by the way. I want to thank everyone for attending and participating in our 10-4 Tech Talk. Jeremy, I want to thank you for the great information, and everyone have a productive day.